All right, I'm going to give you a choice. Would you rather do 1,000 experiments or 10 million experiments? This could be a pause and ponder question. Would you rather do 1,000 experiments or 10 million experiments to derive fundamentally the same information? Well, perhaps you don't even need to pause and ponder, but I'll do something to help put things in perspective. This amount of paper, let's say, would be equivalent to 1,000 experiments. The amount of paper equivalent to 10 million experiments would be this entire ream right here. So, if we're trying to compare workloads here, would you rather do the amount of effort? Would you rather have to do 10,000 experiments or 1,000 experiments? Well, I think it goes without saying, we'd all rather do 1,000. So, where are we going with this? So what does this have to do with fluid mechanics and heat transfer? Well, last time we said that we needed a way, when we had pipe flow, when we had some fluid flowing through a pipe, we might know a lot of information about the system, but we might not necessarily know what H is, right? So we said, hey, we might know some things about this system. For example, like, what is the diameter of the tube? What is the length of the tube? What are some properties of the fluid? For example, the fluid's density, the fluid's viscosity, the fluid's specific heat, and the fluid's thermal conductivity. What is the average velocity of the fluid in the tube, right? We might know all of these things about the fluid, right? Like, these are things that would be pretty straightforward to measure or pretty straightforward to look up, but we might not know H bar, right? Or H, right? So, we might not know this. It would be pretty easy to find these things. This thing is something that's scenario specific, right? So this is hard to predict beforehand, right? We don't necessarily, we can't go on the internet and just look up what some particular H for some particular tube, for some particular fluid, for some particular velocity is going to be, right? That information isn't necessarily readily available to us, but all of these things are pretty easy to find, right? So this is easy to measure or look up, and this is very problem specific, so you're not likely to just find this information just searching, right? So difficult to find beforehand. And yeah, sure, you could set up a situation where you could run an experiment where you set up the precise conditions for your heat transfer and then measured what H was, but that's a pain, right? Like, what happens if it's wrong? Then you need to go back and redesign your entire device, right? So this is difficult to find beforehand, but essential for system design. So what is this lecture going to be about? Well, this lecture is going to be about the idea that, hey, my H bar is basically going to be a function, my heat transfer coefficient is going to be a function of all of these things that are known. For example, tube diameter, length, fluid density, fluid specific heat, fluid thermal conductivity, fluid viscosity, and average fluid velocity. Right? We anticipate H being a function of all of these things. And if you can imagine, let's say I were a budding engineer and I wanted to say, hey, could I come up with what this function is beforehand? I can write a function of 7 variables, and I could, if I wanted to go about formulating what that function is, well, formulating this function would be pretty tricky to do. Let's say I wanted to formulate this function, and I wanted to do so with 10 different values for each of these things, 10 different tube diameters, 10 different tube lengths, 10 different fluid densities, 10 different specific heats, and so on. Let's say I wanted to characterize I wanted to characterize this function by running experiments. And, I might choose 10 different fluid velocities or 10 different viscosities or 10 different thermal conductivities, right? If I wanted to do that and I had to do 10 of these and 10 of these and 10 of these and 10 of these, and wanted to sort of do all possible combinations of all 10 different values for tube diameter and length and density, etc., you could imagine that would basically be 10 times 10 times 10 times 10 times 10 times 10 times 10 experiments, which would be 10 to the 7th, or 10 million experiments. Where are we going to go in the rest of this lecture, right? This would be too many. 10 to the 7th experiments is the whole ream of paper, right? That's 10 to the 7th experiments is this much experimentation. What if I told you that there was a way to cut this down by 4 orders of magnitude? Well, it turns out there is. Rather than forming h bar as a function of 7 variables where we need to test 10 different values of each of them, what we're going to talk about today is a way where I can basically have a ratio with h bar in it, and some ratio of these variables with h bar as one of them is going to be a function of only 3 other ratios. So rather than having h be a function of 7 variables, some ratio of h and some other parameters is going to be a function of 3 other ratios. And if you can imagine, if I did 3 other ratios, that's only going to be 10 by 10 by 10 equals 10, or equals 10 to the 3rd, or 1,000 experiments. So instead of needing to test 10 different values of all 7 inputs, I only need to test 10 different values of the 3 ratios that formulate inputs to this ratio involving an h. And this is much less work. And it turns out that this isn't somehow some approximation of this. For mathematical reasons, we only need to test this. And we're going to talk about basically mathematically why we only need to have ratios of things as a function of ratios of other things rather than h bar being a function of all 7 variables here. So let's hash that out a little bit. So let me share a secret of the universe with you. If you have something that's non-dimensional, if you have some non-dimensional thing, some non-dimensional number, some non-dimensional quantity, that can only be a function of non-dimensional things. And what's the reason for this? Well, so h bar, h bar has units, right? This has units of watts per meter squared Kelvin. So in a sense, this is something that we have that we call dimensional, right? Watts, watts in a sense are dimension. Watts are a united quantity, right? H bar has units, watts per meter squared Kelvin. But something that's non-dimensional, can be a function only of other non-dimensional things, right? So, there's nothing special in the world about meters. It's just all humans. We all talked to each other and agreed that the meter was some particular length. And we all agreed that the Kelvin was some particular unit of temperature. And, watts has joules and seconds in it. We all agreed that time has some certain amount of length of time. But there's nothing special about the meter, nor is there anything particularly special about the Kelvin, nor is there anything particularly special about the second. So what does it mean? If we have h bar, which has units, it's a function of all of these other things that have units. But something that's non-dimensional can really be a function of only non-dimensional things, right? If something that were non-dimensional had units of was a function of something with watts, then watts would have to be this secretly universally special quantity, and that just doesn't exist, right? Watts are arbitrary, seconds are arbitrary, meters are arbitrary. All humans agreed that, that we're all using the same meters and watts and seconds as each other, but I could go to the planet Zarbok and I could say, hey, watts, here are watts, and they're like, no, we don't use watts, we use something else. But if I were to formulate physical relationships in a way that's non-dimensional, right, where instead of having, for example, things with units of watts, if I formulated ratios of things, even if I used watts in my h bar, if I had h bar in a ratio with other things that also had units of watts, those watts would cancel out, and I would be left with something that's dimensionless. So let me amend this right here. This is really a dimensionless. Or you can think of it as unitless. A unitless or dimensionless ratio with h versus 3 other unitless or dimensionless ratios. So if instead of having h bar, which has units, and d, which has units of meters, and l, which has units of meters, and density, which has units of kilograms per cubic meters, if instead I form ratios of all of these variables, a ratio of h and some other stuff, and also ratios of these things that are essentially arguments of this function or inputs to this function, if these are unitless and these are unitless, then there's no more arbitrariness. Then there's essentially no arbitrariness. There's no arbitrariness to watts or seconds or meters or Kelvin. Right? There's no arbitrariness to what these units are. If essentially I form ratios where the watts cancel out and the seconds cancel out and the kelvins cancel out, then I have something that's truly fundamental, that I could go to the planet Zarbok and they'd be like, yep, that's great, and I wouldn't even need to tell them what watts and seconds and meters and Kelvin are, because they could work it out in their own units, and this relationship would still be just as true for them as it is for me. So what do we do this? Something that's non-dimensional can be a function only of other non-dimensional things, because the physics, the true physics on planet Zarbok is the same as it is on Earth, regardless of whether they use different units for watts or seconds or meters or Kelvin. And what does that mean? Well, if these relationships truly transcend whatever arbitrariness we put on our units, but are really some physical quantity here, we only need to get what this physical relationship is between things. And since this sort of arbitrariness of units is something that kind of essentially adds complexity to the relationship, we only need to figure out what the physical relationship is. And this physical relationship essentially is a function of ratios of things. So physics isn't really about these things in particular, but really just about the ratios of these things, because physics doesn't care about the arbitrariness of the units that we put in. So what does that mean? If instead of having h be a function of all of these variables, we could get some ratio of h in a couple of these variables to ratios of these other things, then we'll have something more universal than the original relationship that I put up here. But, what are these ratios going to be, and how did I know that there are going to be 3 of them? Well, I did the annoying thing where the professor kind of already knows the answer, so let's get to this idea on our own route. So there's a precise method. There's a precise method for going from this function of a whole bunch of variables that all have units to ratio to a function of fewer things that have fewer units. And this method is called Ibsen's method, where it's basically going from h bar as a function of a ton of stuff to ratios that are dimensionless. Or you can think of them as unitless. So what do? You basically set up a chart. So, if you talk to real people, they call it Ibsen's method. Because this really involves thinking very carefully about units, and there's a certain baby in the household who really cares a lot about units. If you remember that baby who really cares a lot about units, we can call it baby whose method. So in the context of this class, we'll call it baby you-know-who's method, but in real life, it's called Ibsen's method, who's the guy back in the 40s or whatever who invented it. So what is this method? This method is to basically go from this ratio to this ratio. So what you do is you start with this, and you gradually eliminate particular units. So I'll do a little sidebar over here with what the steps are. Step 0 is write out the units for all terms in a chart. So we said we wanted to formulate h bar as a function of 7 variables. So I'm going to formulate this right here. We said that h bar could be a function of diameter, length, density, specific heat, thermal conductivity, viscosity, and average fluid velocity. That h bar could be a function of all these things. So what are we going to do? We're going to build a chart with all of these variables in it. And so the first thing is we write out h bar, essentially is going to be a function of all these things, and we're going to write out what all the units are for these terms in a chart. So we're basically going to have rows. We're going to kind of have pairs of rows. So h bar, we already said, was going to have watts per meter squared Kelvin. We said that diameter, that's a length, so that's going to have units of meters. L, the length of the tube, is going to have units of meters. Density is going to have units of kilograms per cubic meter. Specific heat is going to have units of joules per kilogram Kelvin. Thermal conductivity is going to have units of watts per meter Kelvin. Viscosity is going to have units of kilograms per meter second, and velocity is going to have units of meters per second. So we write down all the terms, and we write down all the units that each of these terms are going to be. And this is what we have here. Then the next step is choose one type of unit. So we can choose one type of unit to cancel out. And so one type of unit to cancel out might be, for example, I might try to cancel out Kelvin. So I choose one type of unit to cancel out, and one variable or group of variables to use to cancel out. So, for example, I could choose. If I want to cancel out Kelvin, I could choose to use thermal conductivity to cancel out. So I have Kelvin. Kelvin appears as a couple of units in a couple of these things, and I could use one variable to cancel out. So I'm going to try to cancel out Kelvin, and I could basically use thermal conductivity to cancel it out. One thing that you need to be a little careful about is that there are some units that secretly have other units inside of them. So for example, like watts and joules, if you remember, a watt is a joule per second, or a joule is equal to like a watt second. So, secretly there are some units that are actually, other units inside of them. Like the Newton is a kilogram meter per second squared. A joule is a Newton meter. A watt is a joule per second, right? So if you have things like, some of your things have joules and some of your things have watts, you might want to kind of convert. First, you need to sort of convert all of them to the same type of thing, right? So write out units and, basically convert. You could convert everything all the way to base SI units. Or at least just get things like watts and joules in terms of each other. Or at least newtons, watts, and joules all on the same page. So for example here, rather than a joule per kilogram Kelvin, I'm just going to put this as a watt second. Just because I have other watts here, I want to put all of this in terms of watts. So that's something that we should have done as part step 0. So what do? We choose one type of unit, i.e. I want to cancel out, a couple of these terms have Kelvin in them, and I choose one variable or one group of variables that has Kelvin in it. For example, K has Kelvin in the denominator here. So I'm going to either multiply or divide. Right, so here, multiply or divide any units that have Kelvin. I'm going to multiply or divide by however many factors of K needed to cancel out. Multiply or divide by term however many factors needed. So however many factors needed to get rid of those units. So for example, I have velocity here. I don't need any Ks. Velocity doesn't have any kelvins, so I don't need any thermal conductivities here. So this one remains kind of unchanged. Viscosity doesn't have any kelvins in it, so this one remains unchanged. This is the one that I'm using to cancel out, so I'm going to kind of eliminate this, this one from contention now. Specific heat has a Kelvin in the denominator. K has a Kelvin in the denominator. So I can eliminate kelvins by combining a ratio of these two things. So what is that going to look like? I'm basically now going to have Cp over K. Density doesn't have any Kelvin in it, so that's unaffected as is D and L. There's a Kelvin in the denominator here, so basically if I divide h bar by K, then I can eliminate the kelvins from both of these terms. So I choose one type of unit to cancel out. Add one variable. The next step is basically look at new units for each entry. So, the velocity is unchanged. That's still meters per second. Viscosity is unchanged. It's still kilograms per meter second. K has been eliminated from contention. Specific heat is, it's a watt second. So specific heat was a watt second per kilogram Kelvin, and K is watts per meter Kelvin. So if I look at their ratio, the ratio of Cp and K now has units of second meter per kilogram, right? So the ratio of Cp and K, gets rid of a couple of units. Density still has units of kilograms per cubic meter, and these both have units of meters. H bar divided by K, there's watts per meter squared Kelvin, and over watts per meter Kelvin cancels, so H bar over K has units of 1 over meters. And oftentimes what I like to do, just so I can kind of keep a record of how I went from one step to the next step, is I just sort of write out here, what I used to cancel out what. So use K to eliminate, use thermal conductivity to eliminate Kelvin, just as a note to myself to keep track of what I used. But our process is not done. So new units for each entry. Then we basically go back. We go back to step 1, where we choose a new type of unit to get rid of. So, we look out here. I've successfully gotten rid of anything that has units of Kelvin. So essentially now, these relationships here are now invariant to whatever units I use for temperature, right? This would basically be just as true if I worked in Fahrenheit or Kelvin or Rankine or whatever. This is essentially independent of whatever units I use for temperature. So, as of now, formulating ratios of things that basically eliminated whatever system I had for temperature. Now, the next step is I need to go back here and I need to choose another type of unit to cancel out and another type of variable to cancel out that type of unit. So what's that going to look like? Well, for this next one, to go from here to this next line, I'm going to, let's say, let's use viscosity to eliminate kilograms. So viscosity has units of kilograms in it. There are some other terms in here that have units of kilograms as well. I can use viscosity to eliminate kilograms. So I got to extend my chart here. Spoiler alert, I think we're going to need at least to the rest of this page to fill it all out. Velocity doesn't have any units of kilograms in it, so it kind of remains unchanged. Viscosity is what I'm using to eliminate here, and I already got rid of K. This Cp over K has kilograms in the denominator. Viscosity has kilograms in the numerator. So if I take this quantity and multiply it by viscosity, then I'll have canceled out kilograms. So what does that look like? It would basically be like mu Cp over K. So viscosity times specific heat divided by thermal conductivity. I can basically use to eliminate the kilograms that are there. Whereas if a density has kilograms in the numerator, so I need to divide density by viscosity in order to eliminate the kilograms that exist in both of these terms. So now I have, instead of just density here, I have this ratio of density over viscosity. D and L, neither of them have units of kilograms, nor does our H bar over K have units. So what does that mean? Well, velocity still has meters per second. Neither, these terms I've gotten rid of. Mu Cp over K, this was second meters per kilogram, and this was kilogram per meter second. So actually, this term right here has no units. So we've essentially formed a dimensionless quantity. And you can remember, this was something we were kind of working towards. Some ratio that didn't have dimensions being functions of other non-dimensional ratios. Well, we've actually found one of our non-dimensional ratios so far. Stay tuned and we'll find a few more. All right, density over mu ends up with units of seconds per meter squared, and D and L both have units of meters, and H bar over K still has units of 1 over meters. So we're back down here. We just found the new units for each entry. Now we iterate again. And we'll do this a couple of times until we've basically formed only non-dimensional things here and only non-dimensional groups like this one that I've found here. So I'll have either eliminated something from a column or brought it all the way to the point where it's a dimensionless quantity. So what can we do? Well, we need to choose a new type of unit to cancel, and we can do that. I am going to I'm going to use average velocity to eliminate seconds. So velocity is what I'm using. I've already eliminated these two things. This one doesn't have, I've already successfully found one. I've already successfully found one non-dimensional group, so I don't need to worry about this any further. Here I have seconds in the numerator. Here I have seconds in the denominator. So I could do density times velocity over mu. And D and L, neither of those have units of seconds. And H bar over K, that doesn't have units of seconds either. So, so what units do some of these existing terms have? Well, we already didn't have units here. We already found one non-dimensional group here. This has units of, this quantity here has units of 1 over meter. Both of these have meters. And h bar over k, that has units of 1 over meters as well. Well, it turns out basically the only unity things I have left, everything is in terms of meters. So I could do here. I could technically choose any of these. I could choose d, l, or rho v over mu. I could choose any of these to essentially cancel out meters. But seeing here, I have rho v over mu. This is looking an awful lot like something familiar, right? This is looking an awful lot like Reynolds number. The only thing this needs to be Reynolds number is diameter. So I'm going to choose diameter just so I can have the familiar Reynolds number right here. So I'm going to use diameter to eliminate meters as units. And when I do that, well, I already eliminated all of these things. I've already found something in this column here. For this last one, I have rho v d over mu. For this one, I'd have L over D, and of course D is what I use to find this here. And then for here, to eliminate the 1 over meters, I would basically do H bar times D over K. And then, what are the units here? Well, I eliminated this column, eliminated this one, eliminated this one. Oops, sorry, I should be using pink here. Eliminated this, eliminated this, eliminated this. I already found a non-dimensional group here. Rho vd over mu, this has no units. So I've found a non-dimensional group right here. L over d also has no units. So I've found a non-dimensional group right here. And h bar times d over k also has no units. So I've found a non-dimensional group right here. So what does this mean? Rather than having h bar be a function of 7 variables, the ratio of h bar times d over k is going to be a function of this group, and this group. It still essentially has the dependence of all of the variables built into it, either in this ratio or in this ratio. But the benefit is now I need to just worry about how this ratio affects this ratio in terms of experimentally determining these relationships. So, so let me write that out a little bit more in its final form. So h bar times d over k is equal to a function of L over d, rho v d over mu, and mu cp over k. So what are all of these terms here? Well, some of these terms have special names, right? So we already seen a bit in this class that this is what we call the Reynolds number. And it is indeed unitless. Oftentimes people give it RE for Reynolds number, and oftentimes the Reynolds number can sometimes use a different length scale besides tube diameter for it. So sometimes people give it a little subscript d to indicate that d was used as the as it. You can think of Reynolds number as a ratio of fluid inertia to viscous effects. And flows that have lots of fluid inertia and relatively little viscous effects tend to be turbulent, whereas flows that have viscous effects, those viscous effects basically keep all of the streamlines in order and end up with laminar flow here. So Reynolds number is used for laminar flow versus turbulent flow, and we anticipated, if you look back a couple of lectures, we said, hey, h bar H bar is going to be different from whether that flow is laminar or turbulent. Turbulent flows tend to mix up all that fluid a lot more and increase heat transfer when there's all that vigorous churning and mixing and swirling. So, it's unsurprising that Reynolds number is going to have an effect on this H bar. So that's this quantity right here. We see this other term here, and this doesn't really have a special name, but you can just think of it like an aspect ratio. It's essentially a ratio of the length of the tube to the diameter, right? So it's basically just an aspect ratio. And you remember, we talked about the entrance effect, right? A lot of time fluid kind of comes in uniformly and then eventually ends up as parabolic here, and the fluid that was coming in fast ends up getting diverted towards the center. And the fluid that gets diverted towards the center can basically carry some heat with it. But you can imagine for a short tube, this effect occupies a very large fraction of it, whereas for a long, narrow tube, this effect happens just a little bit at the beginning, but most of the tube is basically dominated by by the sort of fully developed profile, or the parabolic profile if it's laminar that it ends up with, right? So this aspect ratio basically says, how important the importance of entrance effect. So the aspect ratio basically dictates the entrance effect. This final ratio here is something that we haven't really talked about yet in this class, but it has a special name too. It's called the Prandtl number. So it's given PR. People call it the Prandtl number. And the Prandtl number, to me, it doesn't really have a ton of a great physical intuitions, right? Like the Reynolds number, the Reynolds number, right? But the Prandtl number, Schmandtl number, right? I don't really, think of this, but I guess you could think of it as a ratio of how momentum diffuses compared to how heat diffuses in a fluid. So, thermal conductivity is basically related to how efficiently heat can diffuse. So fluids that have a high thermal conductivity can diffuse heat quickly, whereas fluids that have a high specific heat, basically absorb that heat essentially before it diffuses farther. So, this K in the denominator and Cp in the numerator is essentially how heat diffusion, how heatly diffusive is this material. So for example, mercury is going to be very different from water, which is going to be different from air. So, this K and Cp is related to the heat diffusivity. And viscosity, you can think, fluids that are very viscous, if I move fluid in one part of the flow, that motion is going to translate very strongly to fluids in the other part of the flow, right? Because basically, you can imagine if I had a blob of honey here and I tried to move one part of the honey, that honey would kind of drag along a lot of fluid with it. Whereas if I move my finger through air, the air over here is relatively unaffected. So momentum diffusivity, because momentum diffusivity kind of plays into how the fluid moves around in the tube, its ratio to heat diffusivity ends up being important to figuring out this H bar times D over K. And then the final thing you can, the final non-dimensional term that we have here, this is a new term as well. This is what we'll call the Nusselt number. And the Nusselt number, people give it NU for Nusselt. Oftentimes, in the same way that Reynolds number, they give a subscript D to correspond to this D right here. We would give a subscript D to Nusselt number to correspond to that subscript D right here. And if your H is an H bar, right, remember we talked about H bar being the sort of averaged H over the whole tube. Oftentimes people, if your H is barred, people give your Nusselt number a bar as well, right? So if H is barred, then people will give your Nusselt number a bar as well. So this is what Nusselt number is. It doesn't really, in the same, in contrast to Reynolds number, where there's this great physical intuition of fluid inertia versus viscous effects, Nusselt number, I don't really like to think of it that way. Just think of it like a normalized H bar, right? So the whole point of this thing was to basically get a way to figure out H, or H bar. So, Nusselt number is basically a kind of intermediate step. It's this non-dimensional intermediate step that we can basically use, so it's basically more convenient experimentally to work out a normalized H as a function of these non-dimensional parameters than a H as a function of a whole bunch of other messy junk. So this normalized H is a function of these other sort of normalized quantities here, some of which have great physical intuitions, in terms of figuring out heat transfer. So what's the deal here? Well, if you want an H bar given, right? So if you want an H bar given all of these things, take all of these things and formulate them as non-dimensional quantities, right? So take all of these things, formulate them as non-dimensional quantities. Then you can basically say, hey, if we want H bar, my H bar is going to be equal to my Nusselt number sub d times k over d, right? So if I have some tube and I know its diameter and I know its fluid's thermal conductivity, I can basically, and I know its length, diameter, and all of this other stuff, I can use all these other things to calculate a Nusselt number. I can basically use these things to calculate a Nusselt number. I can now get some particular number for Nusselt number, and then I can also plug in the fluids K and D, and that gives me all of the information I need to find H bar. So, you're not going to need to do all of these steps to compute your own H, but the very first people who did these experiments to try to figure out what the relationships are between these non-dimensional quantities and H, they basically did this step and said, hey, this is going to be a function of all these things. So when you're looking for functions of H, you don't ever find functions of H, you just find a function of Nusselt number as a function of L over D, Reynolds number, and Prandtl number. So you basically, and then when you want to go figure out your particular H, you just multiply Nusselt number by K over D to get it. So this Nusselt number is basically going to be a function. Nusselt number is a function of L over D, Reynolds number, and Prandtl number. And so we haven't I haven't necessarily told you what these functions are, but I've just said, hey, such a function does exist. So what are these functions? Stay tuned to next lecture, where I'm basically going to build out a chart for a couple of these Nusselt number equations that you'll be able to use for plugging in here, which then you could use to find your own H. All right, so thank you very much for watching, and good luck with your study of heat transfer.